So we evaluate the function at x equals 4.1, y equals 9. This represents a change of 0.1 in the x value, in the x coordinate, and we find that the z coordinate is about 7.1. Matter of fact, in this case it's exactly 7.1. So that the value of the function is the 7 that we started with, and then the change in the value of the function due to the change in the x coordinate is 0.1. Okay, so we add another 0.1 on here, and now we can draw a line segment from here to here, which would correspond to one of the sides, one of the upper, one of the edges of the upper face of this shape here. And we then draw a vector in this direction, because we're going to use this vector to determine the tangent plane in a way that you should be familiar with at this point. Okay, then we, and I didn't label the coordinates here, but just following the instruction, we let y equal 9.2. So y changes by 0.2, and we keep x fixed at 4. So we determine that the value becomes 7.03. We have a change here of 0.03. And we draw the segment along this face of the three-dimensional shape, and we get a vector in that direction. We're going to call the vector that we get when y is held constant, the vector along this face, top of this face, we're going to call that u. The vector along the top of this face we're going to call v. Now we have vectors u and v. For the vector v, okay, the rise is 0.03, the run from this point to this point, the rise is 0.03, the run is 0.2. So we could say the vector 0.2j plus 0.03k represents the direction of this edge of our three-dimensional shape. Doesn't have to be this vector, doesn't have to go from here to here. We could, for example, let our y-coordinate change by 1, and then the z-coordinate is going to change by what? It's going to change by 0.15. How do I know that? Well, I figured out the slope here. 0.03 over 0.2 gives us a slope of 0.15. If we go 1 unit in this direction, that's our run, then our rise has to be equal to our slope. Since the slope is rise divided by run, if the run is 1, the rise has to be the slope. So we have this vector, j plus 0.15k. That's easy if we know the slope, and we can easily calculate the slope from the kind of information we have here. Alternatively, we could make a unit vector out of this one. We could make a unit vector out of this one. And those unit vectors, of course, would be equal. Now, if we want to get the plane of the top of this figure, and that plane is going to actually then be a tangent plane, a plane tangent to the surface that constitutes this graph. Okay, this graph in 3 dimensions, as we've seen, forms a surface. Might be a quadric surface. In this case, it isn't. To get the equation of that tangent plane, we need the coordinates of this point, which we have. It's 497, because of 49 down here, and we go up 7 units, we're at 497. And we then have 2 vectors in that plane. This vector is tangent to that surface. This vector is tangent to the surface. We take the cross product of these vectors, we're going to get a normal vector. A vector normal to our plane. So we're going to have a vector normal to the plane and a point on the plane, which means that we're going to easily be able to determine the equation of the plane. Okay, so if we use the u vector, I plus k, and of course I've got the u vector, it's going to be 0.1 in the I direction and 0.1 in the k direction. That's 0.1I plus 0.1k. We could also use I plus k, just multiply this by 10. We could make a unit vector out of this one. We could make a unit vector out of this one, and these two unit vectors would be the same. To get our unit normal, we're going to use one of our u vectors, any one, and one of our v vectors. And if we want a unit normal, we're going to then divide by the cross product. So we could use any version of u, any version of w. But maybe the easiest, if we use the unit vectors, well, we'll leave that as a question. Maybe it is and maybe it isn't. And we just take the cross product and we calculate the cross product. I haven't done all the calculations. I didn't include the magnitude of this vector. I didn't include the magnitude of this vector down here. We can very easily calculate that. But we very easily then get a normal vector, and if we want it to be a unit normal vector, we divide by the magnitude. So now we have a unit vector, a vector normal to the plane, might or might not be a unit vector, and a point on the plane, so we can find the equation of the plane of these two vectors, which will be the equation of the plane, which is approximately equal, which is approximately identical with the plane of the top of this figure.